When you flip a light switch, you just expect it to work, right? But behind that simple, everyday action, our entire electric grid is going through one of the biggest changes it's ever seen. Today, we're going to pull back the curtain on the hidden tech that's making our green energy future a reality and the brand new challenges that come with it. So, our power grid, a system that's been running on the same basic mechanical principles for like 100 years, is suddenly connecting to all these new digital energy sources. And that raises a really important question. As we push for a greener world, is our grid actually ready for the digital revolution that's powering it all? Let's dig in. I mean, think about it. Every single day, more and more renewable energy is coming online. We're talking solar panels, massive wind turbines, even some really cool experimental stuff like wave power. It's all getting plugged into our grid, and that's fantastic. But they've got a little secret. They don't speak the grid's native language.
Yeah, see, unlike an old school coal plant with its huge spinning generators, these new sources give us power that's, well, it's all over the place. It's variable. So to connect to the grid, they need this special piece of tech that works kind of like a digital translator, changing their power into a language the grid can actually understand. And that translator, well, that's what this is all about.
This really gets to the heart of the matter. It's a fundamental shift in how we make power. It's a story of two different worlds colliding. The old world of raw physical force meeting the new world of digital code. Okay, so the official fancy name for this technology is an inverter-based resource, or IBR for short. An IBR is basically any power source like solar, wind, or even big batteries that uses a special electronic converter, an inverter, to hook up to the grid. You can think of it as the digital gatekeeper for all renewable energy. Now, don't worry, you don't have to be an electrical engineer to understand this diagram. The really important thing to see here is what's at the core of it all. The heart of an IBR isn't some giant piece of spinning metal. Nope, it's a control system, and it's run completely by software. Everything it does, how it reacts to problems, it's all dictated by lines of code, by algorithms, not by the old laws of physics that run a traditional power plant. So here's a good way to think about it. On one side, you have the old guard, the traditional generator. It's like a massive, super heavy flywheel. Once you get that thing spinning, its own physical weight, its inertia, keeps it incredibly stable. But then you have the new guard, the IBR. It's more like a super fast computer. It can react in a split second, but it has no physical weight, no natural inertia to keep it steady. It does exactly what its software tells it to do, for better and sometimes for worse. And hey, this isn't just a cool analogy I'm making up. This table here, it's adapted from a report by the North American Electric Reliability Corporation, or NERC, and it lays out the cold, hard facts. Just look at the differences. Inertia. The old generator has a massive physical rotor. The IBR has basically none. Fault current. Its ability to ride through a problem like a short circuit. The generator is a tank. The IBR relies on really sensitive electronics. It just shows you, crystal clear, that we're moving from a system based on physics to one based on code. But, of course, it gets a little more complex, because not all of these new digital resources are the same. You can actually program them to act in totally different ways. Broadly speaking, they fall into two camps: followers and leaders. Okay, so the vast majority of IBRs out there right now are what we call grid following, and the name says it all. Think of them like a dancer and a huge chorus line. They listen really carefully to the grid's rhythm, its voltage, its frequency, and they just follow along, adding their power perfectly in sync. They're amazing followers, but here's the catch. They can't create the rhythm themselves. If the music stops, they stop dancing. And then you've got this new, much smarter technology, grid-forming inverters. These guys are the leaders. They don't just follow the beat, they can actually help create it. A grid-forming inverter can make its own stable voltage and frequency signal, basically doing the job that those big old spinning generators used to do. It can set the rhythm for everyone else to follow, and that, well, that could be the secret to running a grid on 100% renewable energy. So the fact that these IBRs are driven by software gives us incredible speed and control, but what happens when that software, that digital brain, gets it wrong? And this isn't just a hypothetical question. Let's look at a real-world event that absolutely sent shockwaves through the entire industry. 1,200 megawatts. Just let that number sink in for a second. That is a massive amount of electricity, enough to power almost 1 million homes. And on August 16th, 2016, in Southern California, that much power just vanished from the grid in an instant.
And it wasn't because of a storm or a power plant blowing up, it was because of a glitch in the software.
So here's how it all went down. There was a wildfire, called the Blue Cut Fire, and it caused a few quick, really minor electrical faults on the big power lines. We're talking tiny disturbances lasting less than a blink of an eye. But the software inside hundreds of solar inverters saw that little hiccup in the signal and completely misinterpreted it. The code wrongly calculated that the entire grid's frequency was crashing. So, to protect itself, it did what it was programmed to do. It shut down. Boom. 700 megawatts of solar power gone. That caused the voltage to dip, which then tripped another 450 megawatts offline. A tiny physical blip triggered a massive cascading digital failure.
The official NERC report on what happened was brutally honest. They blamed it on a poorly designed frequency estimation algorithm. The key takeaway here is just incredible. This wasn't a broken piece of hardware. This was a bug in the code. A single software flaw copied and pasted across thousands of devices created this huge vulnerability in the grid that nobody had even thought about before.
That Blue Cut Fire incident was a serious wake-up call. It proved that just plugging in more solar and wind wasn't going to be enough. We also have to make their digital brains, their software, way smarter and tougher. And that's leading engineers down this path of meticulously tuning the future grid.
So one of the biggest puzzles engineers are trying to solve right now is how these IBRs behave on weak parts of the grid. You know, remote areas, far away from the big stabilizing power plants. In those spots, the super fast, super sensitive digital controls inside the inverters can sometimes overreact to tiny disturbances, creating these weird power oscillations that can actually make the grid unstable.
And the solution, maybe not surprisingly, is hidden back in the software. It's this whole process of tuning the grid. First, engineers build these super detailed computer models to figure out exactly what's causing these instabilities. Then, they create these advanced tuning methods, which are basically just really sophisticated software adjustments that change how the inverter reacts to what's happening on the grid, making it less jittery and way more stable. And what's the end goal here? What's the big prize? It's turning these IBRs from a potential liability into one of the grid's greatest assets. With the right code, these things can do so much more than just make power. They can actively smooth out those shaky oscillations, they can provide almost instant voltage support when there's a problem, and they can actually make the entire grid stronger. We can program them to be active, helpful members of the grid, not just passive sources of energy. And that really brings us to the final question we have to ask ourselves. This energy transition isn't just about switching from fossil fuels to renewables. It's a transition from a grid made of physical machines to a grid run on digital code. And while that's incredibly exciting and has amazing potential, it also brings a whole new type of risk. As our world depends more and more on a digital grid, are we really ready for the day the lights go out? Not because of a storm, but because of a single flawed line of code.